Okay, so here we go. Welcome back to part 2 of related rates. We left off here where we had the rocket rising vertically at 5,400 miles per hour. We set up our picture, wrote down our information. We set up the equation tangent theta equals y over 20 that relates all this information. And then we said we just wanted to tweak that and multiply both sides by 20. I think it makes it easier. And now we're ready to go ahead and take the derivative of all this stuff. So the derivative of 20 tangent theta is 20 secant squared theta. Again, chain ruling / tell people you just took the derivative of theta with respect to time equals 1 dy dt. All right. So now we have our related rate. All right. Slide this up here so we have room to continue to work. So now again, I can just start plugging things in. 20 secant of theta. We don't have theta. Theta is something I can go and find. And a lot of you might be going like, hey, let me just go do this. Let me set up our little triangle, that we have over here. And theta. And I know that this is 40 miles. And I know this is 20. And hey, let me just go use, tangent of theta is 40 over 20. And let me do tan inverse of both sides. And use my calculator to find that. And if you're allowed to use your calculator, that is a great idea. You totally can go and do that and go get some value for theta. Some approximation. However, I'm going to say that this type of question is frequently a non-calculator type of question. We need to be able to do this without a calculator. So we're going to come back to that in 1 second. But what we're going to end up doing is we're going to end up finding secant of theta instead, squared. Right? Secant squared. We are looking for d theta dt. And I know that dy dt is 5,400 miles per hour. All right? Now, back to find secant of theta. Well, secant of theta is the hypotenuse over the adjacent side, right? It's a reciprocal of cosine. And I know the adjacent side. I don't know the hypotenuse, but I could go and find it. I mean, if I go and do 20 squared plus 40 squared equals c squared, I can go and solve this, and I'm going to get c is the square root of 2,000. Okay, and again, you can do the math on that. But if that's the hypotenuse, then the secant of theta would be the square root of 2,000 over 20. Okay, hypotenuse over the adjacent. So I don't actually need to go and find out what theta is. I can just find that ratio, and I can plug it in here. And look, I haven't grabbed a calculator yet, but this is working out all real nice for me. If I now go and square everything, I get 20 times 2,000 over 400 d theta dt equals 5,400. If I do some killing off here, 0, 0, 0, 0, I get 20 over 4, which is 5 times 20. I get, I'll just slide up some more. I get 100 d theta dt equals 5,400. And if I divide both sides by 100, I get d theta dt equals 54. Now again, I want to think about my units on this. Theta obviously is measured in radians, right? And then my time, though, here, going back up, what time were we talking about? Well, the only time we've talked about is dy dt was in miles per hour. So this must be in radians per hour. I've got to be careful, though, because they wanted the answer to be in radians per second. Radians per second. So I need to do some unit analysis here, and I'm going to have to change this. And if I go, 54 radians per 1 hour, and I multiply 1 hour, there are 3,600 seconds. I will get my answer in radians per second. And that answer is going to be, if I plug this all in this part you would have to do in your calculator. I mean, I'm good, but I'm not that good to do that in my head. But you're going to get 0.015 radians per second. Always try to use units. Pay attention to your units. Think about your answer. Again, the angle was getting bigger, so it makes sense that my rate is positive. That indicates that it's getting bigger. Okay, so always kind of think about your answer in terms of context again. All right, here we go. Number 3. We only got 4 problems. We're halfway there. Okay, here we go. Number 3. The volume of a spherical balloon is expanding at a rate of 60 pi inches cubed per second. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? Again, read it once, read it twice, read it 3 times, get an idea. Then, draw a picture. Well, this picture's not very exciting, but we've got a spherical balloon. I don't know. I'm not even trying to make that a sphere. We'll just leave it like that. There's my balloon, right? And it's expanding. It's getting bigger. Woo! There we go. That's about a good... And we have a radius on this, right? That radius is changing, so I need an R, right? Don't put a number on that. Anything that's changing, put a variable. Anything that stays the same, you can put the number down. All right. So the volume of a spherical balloon is expanding at a rate of 60 pi inches cubed per second. 60 pi inches cubed per second. The volume is changing, so that must mean that that represents dV dt. The rate at which the volume is changing is 60 pi inches cubed per second. We want to know how fast the surface area is changing. So I'm looking for dSA dt when the radius of the balloon is 4 inches. So that's everything we know about the problem. All right, so I guess if I'm going to have, if I'm looking for the rate at which the surface area is changing, I need to know the surface area of a sphere. You may or may not remember this from geometry, but you are definitely going to want to memorize it now. I won't give out formulas, okay? So 4 pi r squared is the formula for the surface area of a sphere. And so then if I'm looking for dSA dt, well, I take the derivative of this, right? dSA dt is equal to 8 pi r dr dt. Okay, always chain ruling. So if we plug in, I'm looking for dSA dt. That's 8 times pi. I know the radius is 4. Ah, shnikes. The only thing we don't know is dr dt, right? Okay, so I got to find dr dt somehow. How am I going to do that? Well, they gave me this information about the rate at which the volume is changing, so maybe we can use that. Let's come to the side over here and let's use the volume formula for a sphere, which is 4/3 pi r cubed. Again, might want to memorize that. Get to know that. If I take the derivative of that, I get dV dt, 1 dV dt, equals 4 pi r squared dr dt. And now again, I know that dV dt was 60 pi, 4 pi. I know that r is 4. So I can use this to solve for dr dt. I get, moving just over here a little bit, I get 60 pi equals 64 pi dr dt. If I divide both sides by 64 pi, the pi's are going to cancel out. And I get 60 over 64, which reduces to 15 over 16 dr dt. So now that we know dr dt, we can come back and we can plug that in for dr dt. And now we can go ahead and work this out. 8 times 4 is 32, divided by 16 is 2, times 15 is 30. So 30 pi. And this would be, again, going back looking at our units, we were talking inches, surface area is squared, right? Area squared per second. So dSA dt is 30 pi inches squared per second. See, these aren't so bad, and they're kind of fun. Okay, last one. An underground conical tank, vertex down, is being filled with water at the rate of 18 pi feet cubed per minute. If the tank has a height of 30 feet and a radius of 15 feet, how fast is the water level rising when the water is 12 feet deep? All right, so read it 2-3 times, then draw a picture. We have a conical tank, so it's a cone, vertex down, okay? It is being filled with water. Let's make the water blue. Why not? We can. It's being filled with water, right? At a rate of 18 feet cubed per minute. 18 cubic feet per minute. All right, so again, that would be something that's changing. So that is dV dt. The volume is changing. And at 18 pi feet cubed per minute. Okay. If the tank has a height of 30 feet and a radius of 15 feet, so these are things that are not changing, so I can put on my picture, a height of 30 feet and a radius of 15 feet, how fast is the water level rising? Man, we're going to need more colors here. Here's the water level, right? Oh, I should have used blue again. Oh, well. Here's the water level, right? That's the water level. That's changing, right? It's going up. So I need to call that a variable. I'm going to call it h. Okay? How fast is the water level rising? So we're going to look for dh dt when the water is 12 feet deep. Again, that is changing, so don't put that 12 on the picture. When h is 12 feet. Okay? So now we've kind of got all the information. We have a picture kind of drawing what's going on here. I've got the height and the radius of the tank on there that are consistent. I've got my water level that's rising, so I have a variable for that. And I have everything kind of labeled that I know. All right? So now I need to go ahead and get into this. It looks like we're talking about volume, so I might want an equation for the volume. The volume of a cone, another equation you need to know, is 1/3 pi r squared h. Okay? I'm going to go ahead and take the derivative of, well, I'd go take the derivative of this thing, but if I take the derivative of this right now, I've got r's and h's in it. They're multiplying together. I'm going to have to use product rule. That's going to get ugly. I'm going to get dr dt's, which I don't want. I do want the dh dt's. So that's kind of a mess right now. Before I take the derivative of this thing, I think I need to go back and I'm going to want to rewrite this all in terms of h's. All right? So here's how we're going to do that. Okay. What I drew down here is I drew like a little cross section of our cone, right? If we kind of cut it and look at it here, I've got the radius 15 and the height is 30, and then I have the radius, which is changing, of the water, so I put an r in there, and the height of the water, which is h, which is again is also changing. Okay, and so when I draw it like this, I guess we end up with some similar triangles, right? So again, using our geometry, I know that similar triangles are proportional. So I can write a proportion between all this stuff. 15 to r is equal to 30 to h. Well, there's a bunch of different ways you can set up that proportion as long as it's true and you keep corresponding sides together. And now if I go ahead and multiply, I get 15h equals 30r. Or again, we're trying to write r in terms of h. So r equals h over 2. All right. Now that I know that, we can come over back to our original equation here, and I can plug in for r. V equals 1/3 pi. R is h over 2 squared times h. Or now we get V equals 1/3 pi h squared over 4 times h. Or V equals pi over 12 h cubed is my equation for pi in terms of h. And that's going to be a lot nicer now to take the derivative of. Okay? dv dt equals pi over 4 h squared dh dt. Okay, hopefully I didn't do too much too fast for you there, but 3 times pi, 3 over 12 is 1/4, and that's how I got to that right there. All right, now I need to plug in all my information. We know that dv dt we said was 18 pi. It was written above. Pi over 4. I know that I'm doing this when h is 12 feet. And I need to find dh dt. And so now I've got everything I need to go ahead and solve for this. If I multiply out and work this all through, because I'm running out of time, I'm just going to say you're going to get, and you can verify me here, but dh dt equals 1/2. Okay, this h was measured in feet, and our time was measured in minutes. So 1/2 feet per minute is my final answer. All right, boys and girls, these are just 4 examples. Now go try some of these on your own. There's many more. Have fun with related rates. They're really a good time. Bye now.